Okay, hi everyone. In this lecture, we're gonna talk about the characteristic methods for Hamilton-Jacobi equations, and I mean that will be done quickly because we have done that before, and then we will go into talking about local wellposedness theory for Hamilton-Jacobi equation via characteristic method. Um, so let me start with sort of recalling quickly and to provide a general picture for the characteristic method for Hamilton-Jacobi equation. So let me start with one, which is characteristic uh, method for Hamilton-Jacobi. Right, so we will start with a more general situation, and then when we talk about local verboseness, we will talk about a more uh, a simpler version, but the result is quite clear. So we start with this equation that we have seen so far. So we have ut plus h of x du equal to 0. And we are given the initial condition u of x0 equals to g of x on Rn. And again, very quick recap about the method characteristic is that we would sort of start with the xt coordinate, so xt, and you would try to start your characteristic at any given point, say x not 0, and then you would try to uh, find a characteristic curve. In this case, the curve is xt for t greater than equals to 0, and you try to solve the equation along this characteristic curve, right? um, and if you can solve a system of ODEs on this characteristic curve, then you are able to determine the solution along this curve, and the hope is that you can try to do so along all these possible curve, right? And hopefully that by doing so you can find a solution along the curves. Okay, so along this curve, let me again, I mean we have talked about this, but let me recall quickly again the curve xt t greater than 0 is called a characteristic, right? That's what we know. And we would define p of t equals to the gradient of u in x. Okay, sometimes we would write this is gradient x of u of xt. And you could define z of t equals to u of xt along the characteristic. Okay, and we have already derived the general formula for characteristics. So let me just recall um, the ODE system for the characteristics uh, is we chose x dot of t equals to dph of xtpt. Okay, uh, that's what was chosen, right? We chose it this way so that things cancel out, so that we have a nice uh, closed form system, and we have p dot of t equals to minus dxh of xtpt. And finally, we have z dot of t equals to pt dot with dph xtpt minus h of xtpt. Okay. with given initial condition that we started with x0 equals to x naught, right? We started with p0, the gradient, so it's d of g of x naught, because g is a given initial condition, and also we are given that z of 0, which is just g of x naught, the initial condition evaluated at x naught. And again, if, let me write down, so if, what, okay, why is it changing? If we can solve this system of 2n+1 equations of the ODEs, then we can find the value of u along the curve, right? The value of u along the curve here is just z of t, right? It's 2n+1 equation because the first ODE here, this one has n equation. The second ODE has n equation. X and t are vectors in Rn, and z has one equation. It's z is a scalar. It's just a real number. So that in total gives you 2n+1 equations. And as a matter of fact, let me note that the first two n equations give you the Hamiltonian dynamics, right? So we talked about that. The first two n equations give us the Hamiltonian system. So this is a very famous ODE system, appears in Hamiltonian mechanics or Hamiltonian dynamical system, right? And people have studied this a lot. This is very important. So I have x dot. Let me omit the t equals to dp h of xp, and p dot goes to minus dxh of xp. So this is a very important Hamiltonian system, and it has been studied a lot in the literature. So okay, let me not go too much into that, but let me recall very quickly a simple lemma, just a very quick recall so that everything is consistent, is that we would have the t maps to h of xt pt is constant. And this means that we have conservation of energy. Again, here the Hamiltonian represents the total energy. Okay, so the proof is very simple, right? It comes directly from the Hamiltonian dynamics. We just to prove anything is a constant with respect to some variable, the easiest thing to do, or one of the easiest thing to do, is just to prove that the derivatives along those variable is zero, right? So I'm going to compute d over dt of h of xdpt. Okay, so measure the change in time of this Hamiltonian. So by using chain rule, I would have t appears in both x and p, right? So if I differentiate in x, I would have dx of h dot product with x dot of t, okay? And if I differentiate in p, I would have dp of h dot product with p dot of t, right? So all together, now using the ODEs, x dot is dp, so I have dx of h dot with dp of h, and p dot is minus dx, so that's minus dp of h dot dx of h, which is 0. Okay, so that gives me conservation of energy, right? So maybe let me give you example. I mean, just wait, add a page. Okay. This example was already discussed, but again, I mean, let me just recall. Um, so okay, maybe so I should note that H here is the Hamiltonian. Typically represents the total energy. Okay, so let me give you an example. This was already discussed, but let me recall it so that everything is on the same page. All right, so the example I'm going to consider is that let's say that a particle, uh, let's say a trajectory of a particle um, uh, with a unit mass, right? So with unit mass. So unit mass here, of course, I'm assuming that the particle has mass 1. Um, so P here represent for the momentum, right? So we have the normal formula P equals to mv, and this equals to v. P is the momentum, and v is the velocity of the particle. Okay. Um, so the Hamiltonian I'm considering h of xp. Again, remember that we have x represent for position and p represent for momentum. This is the total energy, so it's equal to kin, wait, kinetic energy uh, plus potential energy, right? So kinetic energy is 1/2 mv square plus, let's say potential energy is given to us v of x. And this is given to us, right? And because we have m here, m equals to 1. So that can be written as h of x is simply 1/2 v square or p square, right? P square plus v of x. Okay. So kinetic plus potential energy. The potential is given to us through whatever measurement or something. Okay. Um, Now let's write out our Hamiltonian system. ODE. I would have x dot equals to dp x of xp, right? Again, you are given that dph of, sorry, h of xp is 1/2 p squared plus vx. So if I differentiate in p, then I would have 1/2 p squared being differentiated, right? That would give me p. So x dot equals to p, and p dot equals to minus dx of xp. So when I differentiate in x, I only differentiate in v here, right? So it's minus dv of x. Okay. Um, so this gives me a very beautiful system that x dot equals to p and p dot equals to minus dvx. Okay. Um, and you can see that this is natural, right? When you differentiate the position, you have velocity, or in this case, momentum, because m equals to 1. Um, and the p dot equals to minus dv of x, meaning that you go in exactly the steepest gradient descent, right? You go in directly minus of the gradient of the potential, right? So that's kind of the optimal part that you would go, okay? Um, and you can see that from here, of course, we can, this would give us that I would have, let me change the other color. So this could give me that I would have x double dot is equals to p dot, right? Equals to minus dv of x. Okay. Um, and you can see that This is exactly, remember, as I said, right? V is a given potential energy. So the force is going in the steepest gradient descent, right? So minus dV of F is nothing but F of xt, right? Uh, okay, maybe let me put T everywhere so that is clearer. Okay, so X double dot of T is equals to P dot of T equals to minus dV x of T is equal to F of xt. So this gives me exactly the second Newton's law, right? I have F xt equals to ma, which is m times x double dot of t equals to x double dot of t because m equals to 1, right? So that's exactly Newton's law. Okay. And further that wait, what? Okay. And further that as we noted, right? And further we have conservation of energy, right? Conservation of energy that I have 1/2 pt square plus v of xt equals to a constant. So let me say this is a constant. This is the so-called energy level. Okay. Um, and of course you can you know uh, for this given energy level, so sometimes you can draw the phase diagram to see uh, the corresponding position of x and p with respect to that energy level. So let's say that um, for example, if this is kind of the energy level uh, um, of 1/2 p squared plus v of x equals to c. I'm just drawing a random picture here. Then that means that if you start at this point, p0, x0, then your trajectory is always running in this energy level, right? So it's really important to be able to understand the sort of the dynamical behavior of those curves as time goes to infinity, for example. So that is a big question in dynamical system. Okay. Um, that's exactly the very simple idea of characteristic method and a corresponding example for the classical mechanics Hamiltonian. So now let me go to a next situation which is simpler to be discussed, and then we will focus on that today. Okay. So let me now. Okay. So the second part is the a simpler situation in which that we know better the dynamics. So I would say that this is spatially homogeneous Hamiltonian. Spatially homogeneous Hamiltonian meaning that it's homogeneous in space, or meaning that it's independent of the spatial variable x. So, okay, that means that let me so by let's say abuse of notation, we just assume that h of xp now is only dependent on p, so it's independent of x. Okay, independent of x. That's why we say that it's spatially homogeneous. And I want to talk about this situation, and we want to understand in this situation what happens to the method of characteristic, and w- I mean, what can we do here? Can we go a bit deeper here, right? Okay. So because h of xp is equal to h of p, then what I would have is that I would have d h of x is equal to 0, right? Because there's no x here. And dp of h is nothing, just the gradient of h in p, right? I mean, because there's no x anymore. Okay, in this scenario, then I would have that our ODEs from the meta characteristic become, I would have x dot of t goes to dph, right? dph was computed right above. I would have is equal to dh of pt, right? I would have p dot of t equals to minus dh of x, which is 0, right? Again, because there's no x dependent in the Hamiltonian. And I would have z dot of t equals pt dot with dh of pt dp minus h of pt. Okay, that is our Hamiltonian dynamic. Sorry, our OD system from the method characteristics. The first two give you the Hamiltonian dynamics. The third equation, z dot of t, gives you the changes of the solution along the characteristic curve. All right, so now as you have p dot of t is equal to 0, meaning that p is not changing, right? So if p is not changing, then I would have pt equal to p of 0, right? And remember that p of 0 is the gradient of g at 0, at x0. Okay, so that is that. I would have then x dot of t would equals to dh of pt, which is p0. So, and it's dg of x of 0. Okay, so this is good because it means that the p is not changing, right? And it implies further that x dot is a constant vector, meaning that x is a straight line, right? So it's a straight or array. So the characteristic of straight lines. That's really important. And then I also have z dot of t is clear. It's also a constant along the curve, right? So p is dg of x0. Okay, I'm out of space. Oh, let me try to write that. dh of dg of x naught minus h of dg of x naught. Okay. Yeah, so Sam, z dot is also a constant, meaning that this z is also just changing. Uh, I mean, it's linear along the characteristic, right? So maybe let me write down a little bit. So this implies that I would have what? I would have xt would equals to x of 0 plus t times dh of dg of x0. Beautiful. Okay, let me move z up. So I have zt equals to z of 0, which is g of x0, plus t times the slope, in this case, dg of x0 dot with dh dg of x0 minus h dg of x0. Okay, so it's also a linear function. Beautiful. And I have pt is equals to p0 as for ot, which is dg of x0. Okay, very good. So let me try to draw a schematic picture here before we go further. Okay, so let's say we start from x naught here. Um, we are given the initial condition g, right? So given g here, I know the gradient dg, and I know what is the direction dh evaluated at dg of x naught. So our characteristic curve is just a straight line right here, right? So this is xtt. So characteristic, and the value of the function is also of the unknown is also just changing linearly along the characteristic line, right? In this case, a line, and maybe here also I would have that is here something. If I start from x1, it's like this. However, it could be the case that if I start from x2, yeah, right, it might run into those, right? Or if I start from x3 here, it might behave like that, right? So I can have various different behaviors. And as always, we are worried in the fact that if characteristics run into each other, what happened, right? And we want to understand in this lecture that we would like to be able to characterize when, until when that characteristic are not running into each other, right? So maybe let me write out the question for today is that we want to do local wellposedness theory in this case, right? So the question is until when that the characteristics characteristics don't cross each other. Okay, the moment that they cross each other, we are in trouble. Why? Let me explain. You see that, let's say that the characteristic from x0 meets with the characteristic from x3 at this point. Okay. You also see that along the characteristics, p is a constant, right? P is a constant vector. So at this given point, I would have pt would be equals to both. Uh, okay. Uh, okay, let me write. pt would equals to dg of x naught, or pt would equals to dg of x3 at that intersection point. It's not clear, right? And from the situation, you see that the dg of x naught and dg of x3 must be two different vectors, right? Because if they were the same vector, then you look at the first equation here for x. If dg of x naught is equal to dg of x3, then that means that the two characteristics from x naught and x3 are parallel, right? So okay, maybe let me write it down. So when two characteristic, say from emanating from x0 0 and x3 0 cross each other, we must have that they are not parallel, right? And they are not parallel, meaning that dg of x naught is different from dg of x3, right? The gradient must be different, but when they intersect, then how do I choose p, right? P is the momentum, or in this case, the gradient of the function. So that means that the function has some gradient jump, and this is a big deal later on in the theory of Hamilton-Jacobi equation. In viscosity solution is to understand the gradient jump, and at least that in this case is not clear if we only look at the characteristics. Okay. Um, of course, in this lecture, we are not going that far. We will only try to see until which time there is, we're going to show that there's some small time period in which that the characteristics don't yet run into each other. And for that, we would have a wellposedness theory. And we will leave the other part for a more advanced course, right? I mean, that is more on like viscosity solution, Hamilton-Jacobi equation. There's a lot of deep sort of study along that directions. but also there's still a lot of important open questions addressing like understanding the gradient structure, understanding, when characteristic running into each other, then there's a gradient jump. What is the mechanism for this kind of gradient jump? Right, that's exactly the situation that you see here already in this picture. Okay, good. Right, so let me now write down exactly the equation and then wait. Okay, so as said, we would only have h equals to h of p, right? So we have the second equation for our lecture today is I only have ut plus h of du equal to 0 in Rn plus 0 infinity, and I have the initial condition u of x0 equals to g of x on Rn. All right, so as noted, right, the characteristic of straight line. So our goal is that this is time x, this is time t equal to 0, t, and our goal is to determine there's a time capital T that until this capital T characteristic are not intersecting it with each other. Maybe they're gonna intersect, but at later time. Like this is a picture, right? So I mean, so they may intersect, but only later, not right away. Okay. Let me see. How should I? Um. Okay. Maybe it's best if I write down exactly the theorem right away, and then I'll give you a proof. Okay. So this is the theorem of the day. Theorem. Okay. So assume that H, the Hamiltonian, and the initial data G are given function in C2 of Rn. So they are C2. And for simplicity, let me assume all this assumption can be relaxed a bit, but assume further that, let's say, the gradient and the Hessian of G about it. So dg um, and d square of G, the gradient and the Hessian about it on Rn. Okay, everything is bounded. Let's say they're bounded by the constant c, or I mean some big numbers, whatever. Okay, so I write out the theorem. It might now look a little bit complicated, but I'll explain the notations, and then we will. I mean, maybe we work through the 1D case first for you to see the ideas, and then we will write out the proof for the general case. Okay, I let the capital time t to be supremum or small time or possible small time little t greater or equal to 0, so that In, this is the identity matrix of psi n plus t times d squared h evaluating at dg. This is a Hessian of h, which is a matrix of size n times n. It's a square matrix. I multiply with a matrix also size n times n, so multiply d squared g. Um, so if this matrix, right, In is a square matrix of psi n, and T is a scalar, multiply with a matrix of size a square matrix of size n. So if this matrix is invertible, table for all z in Rn. Okay. Yeah. So we define capital T to be supremum all small possible t, in which that I have the sum of In plus this square matrix is invertible for all z. Then I say that then say hmm, Yes, okay. Okay. Then I would have that um okay, maybe let me explain. So here IN is the identity matrix is of size of size n. It's a square n by n matrix, identity matrix. Okay, so if this is the case, then equations 2 um, has a unique solution determined by the method characteristic. Okay. Um, you define in C1 in Rn cross 0 up to capital T. Okay, maps to R. Okay, I can, yeah, including 0 is fine, excluding capital T. Okay, so this is the statement of our theorem. Of course, it might look a little bit complicated for you, right? Because if you first see this, it's kind of like, yeah, I mean, so maybe let me explain a little bit. Let me give you a remark and then I'll give you an explanation in 1D and then we go to the proof. Okay, so a remark first. Remark. Okay, so note that we are given that, okay, let's say dg of z and d squared of g of z, those are bounded in for all z, right? That's what given to us in the hypothesis, okay? And h is a C2 function because dg and d squared g is bounded, then we would have that d squared of h acting on dg multiply in terms of matrix with d squared of g of z. This is bounded, right? So they are, they we are just multiplying bounded matrices. So it gives me another bounded matrix, right? So this means that so if t greater than 0 is very small, I would have t times d squared of h acting at dg of z. D squared g of z is small, right? Because I'm multiplying a bounded matrix with a constant t that is small and everything is small. So clearly I would have that the identity matrix plus some small matrix is invertible for small t. Okay. Yeah, so it's sort of clearly invertible for small t. So what is the problem is that as t getting bigger, 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 maybe there's a threshold, big capital T, so that it's not invertible anymore, and that is our capital T, right? But for small t, it's always invertible, meaning that you know our problem is solvable at least for some positive time. Okay, so we see that capital T is greater than 0, um, right? It's solvable for at least some amount of time. And it's possible, it's possible that capital T can be plus infinity. Okay, it's possible. It's not a problem. Okay. Uh, yeah, maybe to make it really rigorous, maybe okay, let me change this one a little bit to make it very rigorous. Eh, So, okay, it's invertible. Maybe let me change this one to S. Just to make our definition very rigorous. So I'm just changing it. So I have in plus S times d square of H acting at dg times d square of g of z is invertible for all z in Rn and all S from 0 to little t. Okay, so just want it to be invertible for all Z and S so that nothing is going wrong. Yeah. Okay, good. So that is our first remark. Our first remark saying that it's very small. If S is very or T is very small and everything is fine, right? Um, and the second remark I want to make, and then we will connect it to the 1D case. Let's say this is remark one and remark two, and then we will work on that. Is that when n equals to 1 in one dimension, because this is the Hamilton-Jacobi equation is different because we are working on the multi-dimensional case, right? So we have to work with matrices. When we work with conservation law or Burger's equation, it's in 1D. 1D is simpler. I mean, right? So when n equals to 1, you can see that what it means here by an invertible matrix is very simple, right? Then I would have that uh, you know saying that one is invertible, meaning that the requirement of invertibility uh, uh, is equivalent to, right? It's equivalent to the fact that in is just one, right? So s 1 plus s times h double prime, right, in 1D, g prime of z multiply with g double prime of z is not zero. That's simple. Okay. So in 1D it becomes something very simple for z in R and for s in 0 up to time t. Okay? Yeah. Nothing more, nothing less. Very simple. All right. So now let me discuss this situation in 1D first, and then I'll give you a full proof in n dimension later. Okay. So let me start with, okay, discussion in one dimension. Okay, so again, this is a very simple situation. Xt, right? We want to quantify, if we start this curve from x1 and x2, we want to quantify when they are intersecting each other, right? I want to claim that if they intersect each other, then this little t should be bigger than capital T, where capital T is something that was defined, right? So let's do that. Um, so let's assume that the characteristics from x1 0 and x2 0 intersect, right? At a point called x, intersect at say x bar t bar. Okay, this is t bar. Then let's just say that they intersect at a point x bar t bar, right? Let me recall to you the characteristic. So it's written, where is it? Yeah, the characteristic is written here, right? You have xt is just x naught plus t times the slope, right? Okay, so let me write down now. That means that I have x bar is equals to x1 plus t bar times the slope dh of d no dh h prime is in 1D. x h prime of z prime of x1. That's what given to me, right? But because they intersect, so that is also equal to um, x2 plus t bar times h prime g prime of x2. Okay. And of course here, because so let me remark exactly the point I said earlier. So as x1 is not equals to x2, the two quantities above are the same. This can only happen if g prime of x1 is not equals to g prime of x2, right? Otherwise, if they are the same, then you would have two parallel characteristics. Yeah, so you have this equality, you just subtract, right, and combine them together. Um, so I would have x1 minus x2 plus t bar times h prime of g prime of x1 minus h prime g prime of x2 would be equal to 0, right? And now I'm gonna divide everything by x1 minus x2 and try to use the mean value theorem, right? Okay, so divide everything by x1 minus x2, I would have 1 plus t bar times h prime g prime of x1 minus h prime g prime of x2 over x1 minus x2 equal to 0. I can divide because I have x1 is not equal to x2. Okay, so then by the mean value theorem, there would exist a point z between x1 and x2 such that I would have, you know, um, this is, I'm just using f of x1 minus f of x2 over x1 minus x2 is equal to f prime of z at a point z in the between, right? So that's exactly that. So I would have 1 plus t bar multiply with, I differentiate h prime of g prime, right? So that would be h double prime g prime of z by the chain rule, g double prime of z equal to 0. Okay. Now let's go back to the previous page that we have written it down. This is exactly that, right? I mean, this condition, maybe let me put a box here. This condition here, and down here for 1D case is exactly that condition, right? We were talking about that for all s between 0 and t, this can't happen, right? So you can see that this equality happens if and only if, uh, so this implies that we must have t bar must be greater than or equals to capital T, right? Because the definition was that capital T is a supremum of the time in which that I would not see yet, uh, um, um, I would not yet see um, the zero, right? I would not yet see that 1 plus s times h double prime of gz multiplied with g double prime of z is yet 0, right? They have to be not 0 for all s in 0 to t, and capital T is supremum of all that little t, okay? Um, so, um, so you can see that this is exactly the case, right? Intersection can only happen if your time is greater than equals to, yeah, greater equals to capital T, right? Okay, so more or less, I mean, this is not a full proof. We have kind of like a a an intuitive proof in 1D, right? As I said, this is not yet a full proof because the statement of the theorem is that not only that characteristics are not crossing, but that we have the solution that is unique, and it's C1, right? I mean, it's unique, meaning that your characteristic have to foliate, has to cover everything in this strip for time 0 to t, and that you have to prove your solution is C1. But nevertheless, this is kind of an idea, okay? So now let me give you the full proof of the theorem. And in order to do so, I would need to, because it's in multi-D, so I would need to use some of the results on inverse mapping theorem and implicit mapping theorem. So let me state, I will accept one of them. Okay, so some tools. Let's see what discussion on D, theorem one. Okay, so let me say that some tools to prove theorem one. Some tools to prove theorem one. Okay. Again, I mean, I would need inverse mapping theorem and implicit mapping theorem. So let me just state them. So theorem, this theorem one. So let me say this is theorem two. I will accept it. This is called inverse mapping theorem. This is often learned in multivariate calculus and maybe routine and analysis too. Okay, so let F mapping from Rn to Rn be a C1 map, right? C1 vector field map. C1. Okay. Suppose that there exists a constant m big enough such that our map is never. No, no, no. Sorry, this is. I take it back. This is for the inverse implicit mapping theorem. Um, um, okay, yeah. So assume app is proper. That is, I would have that app inverse of a compact set is compact. It's compact uh, for if k in Rn is compact. Okay. Uh, so you might wonder what is this assumption, right? Because if you have f is C1, then that means that f is continuous. And K is a compact set, which means that K in this case is open, sorry, closed and bounded, right? Because it's in Rn. So if K is closed and F inverse of K is closed, right? However, it doesn't mean imply yet that F is inverse of K is compact because it can be unbounded, right? So this assumption essentially assumes F is proper, meaning that F inverse of K needs to be also bounded, right? The moment that you have is closed and bounded, then it's compact in Rn. Okay, so I need to put this assumption that F is proper. Okay, and I assume further that the determinant of F of the determinant of the df of x is not zero for all x in Rn. F is a vector field, so df is a matrix of size n times n, right? So we assume that the determinant of df is not zero. Then f is a global C1 diffeomorphism. Okay, so it's one to one and onto, and it's diffeomorphic. You take any set, it maps to this set, and it's in a C1 way, and vice versa. That F maps from this set to the other set, and F inverse map this set to this set. Okay, yeah. So that is our theorem. We accept it. And this is often done in multivariable calculus and baby routine. Um, the local result is clear. And the global result that I to have F is a global C1 diffeomorphism, then I would again I would need to assume that F is proper, right? So and assume a little bit more because not only that uh, basically it's that I take a compact set, then it maps to a compact set, and vice versa. That if I take a compact set here, it has to map to the map back to a compact set. Okay. Um, so we accept this, and now from this theorem, accept theorem two. Okay, so now let me write out theorem three based upon theorem two. This is something called implicit mapping theorem. Okay. Uh, oh yeah, I should have changed color. Anyway, so this is normally stated like following. So let a map phi that is mapping from Rn cross some interval AB mapping to Rn. Okay. Uh, be a C1 map. Be a C1 map. Okay. Assume that there exists a constant m greater than 0 such that the alpha function, you know, is m close to the identity map. So meaning that, you know, identity map, right? So it's kind of like a fixed distance bounded within that to the identity map. It's a normal assumption. This is less than equals to m for all xt in Rn plus 0 plus AB. Okay. And then suppose further that the determinant in the in the x variable phi of xt, I'm only differentiating in x here, right? Then it's still an m by m matrix. Assume that the determinant is not 0 for all xt, right? Then we would be able to find a map C so that when we plug in phi composite C would give you identity matrix in X, okay? Then uh, then there exists a map C mapping from, let's go capital C corresponding to capital phi, a mapping from Rn cross AB maps to Rn such that we would have uh, uh, a C1 map. There exists a C1 map such that I have phi of C of xt at t would equals to x. So okay, so it's kind of identity in x, right? Okay. So let me give you a proof of this. The proof of this is a quick applications of so application of the inverse mapping theorem. Okay, so it's really a quick application of that. Okay, so yeah, let me write down. Yeah, maybe let me see. Okay, yeah. I'll skip the fact that the proof that is proper because very simple. Um, so let's see. Okay, yeah. So let me fix t in AB first, right? Because I'll first fix the time first, and then I will define the map for each of the fixed time. And then I'll come back to show that the map is C1 in both time and space. Okay, so let f of x just to be phi of xt, right? So we fix the time. Then as we have f of x minus x is less than equals to m, it's um, easy to see that f is proper. I mean, I just don't want to write down, but because you see that it's bounded away from the identity map, right? So f inverse of a compact set has to be bounded, and as I said, it's already closed, so it has to be a compact set. That's the whole proof. Um, okay, so I just don't want to write down. It's proper. Then and further, remember that we have determinant of df of x is nothing but determinant of dx phi of xt that is not zero, right? Not zero. So this implies right away that that f satisfy the assumption on of theorem 2, right? So this implies that f is a global C1 diffeomorphism, right? Right. Again, this step is quite simple. We just fix t. We do not so much with it. Um, so if there's a global C1 diffeomorphism, that means that there exists a function c when the time is fixed, such that we do have that f of c of xt, and f of c of xt in this case is just nothing but phi of c of xt would equals to x, right? Okay. So that's good. We have already shown the existence of C. Okay. What is missing now is that we need to verify that this function C is C1. Okay. So to verify C1, it's also very simple. So now we define a new function phi tilde of xt would be, now we add the t variable to it, right? So because remember phi is a function mapping from Rn plus 1 to Rn, so we're missing one variable. Now I add that variable to it. So I let phi tilde of xt to be phi xdt. So I add one more variable to it to make it mapping from Rn plus 1 to Rn plus 1. And c tilde of xt to be c of xt. So I add one more variable to it, okay, to make it exactly from Rn plus 1 to Rn plus 1. Let me check that. Okay. Um, then, as noted, right, we would have, let me write down, I would have phi tilde composed with c tilde acting on xt is equals to what? This is c tilde of xt, let me write phi tilde, c tilde of xt is given to be c of xt, t, right? And phi tilde of c tilde of xt is nothing but xt, x, right? No, let me write slowly. Equals to phi of c of xt, t, right? That's by definition. And again, phi of c of xt, t is x, right? So, uh, and sorry, yeah, and t. So this is just xt. Okay, so this implies that I would have phi tilde composed with c tilde is the identity map, right? And it's the identity map. And further, I compute that the full gradient of phi tilde xt would be dx phi xt phi t of xt 0, 1. And clearly that you compute the determinant d phi tilde of xt would be equals to exactly determinant dx phi of xt. This is not 0, right? Then by the inverse mapping theorem again, you implies that so by theorem 2, the inverse mapping theorem, you implies that c tilde is c1, right? So this implies that c is c1. Okay, so we are done with the implicit function theorem and inverse function theorem. Implicit mapping theorem and inverse mapping theorem. Now that I'm ready, now I can just write out the proof, right? The proof is actually very simple because we have prepared everything that was needed for us, right? So let me write down now. Finally, I have now sketch a proof of our main theorem for today, right? Theorem 1. Let me recall the characteristic if you forget it. So let me now x of t, let me denote it by capital X of xt, that we start at the point x at and at time t. So this is going to be x plus t times dh dg of x. This is our characteristic. So meaning that if we start from x0 here, we would end up with this point. This is xtt, or I write it to be capital XT. Okay, so that is the point that we end up with. And we have this map, right? So we have this map capital X. Uh, is now the map that I consider map mapping from Rn cross 0t maps to Rn, right? I take little x and t, I map to capital X. Xt is the location of our characteristic at time t, right? X plus t dh dg of x. This is a C1 map, right? Because H and G are given to be C2, so this is a C1 map. Okay. And now I need to verify that it satisfies the assumption of theorem 3. I'm going to apply theorem 3, right? Um, and to verify that it satisfies the assumption here, I noticed that the fact that it's bounded by a constant to an identity map is very clear, right? So, um, so I note two things. Notes. First is that capital X minus X, this is just T times this DH. No, T is even a positive number. Just T times this. And again, we assume that G is dg is bounded, so this is less than or equal to m for sure. For T less than capital T. And the second thing I need to check is that I need to check what is the determinant of dx of capital X of xt, right? You differentiate in x, this is exactly determinant of in, right? The first x gives you in. The second one here, you use the chain rule plus t times d square of h dgx d square of g at x. And this is not 0 for x in Rn and t in 0t by the definition of t, right? So it's not 0. And let me recall here, you can look at the implicit mapping theorem. It satisfies exactly the assumption that we put, right? And hence we can find that uh, So we can apply theorem 3, which is the implicit mapping theorem, to find that to find a map Z mapping from Rn cross 0t to Rn such that I would have x acting at Z of xt, t would equals to x, right? For xt in Rn cross with 0t. Okay. Yeah, 0 can be included, excluded doesn't. Yeah, included is fine. Okay. Um, all right. So what does it mean? This is x of zt, sorry, x of zxt at t equals to x. So maybe let me draw a picture here. Now it becomes very clear. This is xt. What we just showed that there exists a map that if we start at, oops, if we start at this first emanating point, this is z of x t 0. If we start at this point, then it would map to the point xt, right? So clearly, this gives me exactly now the formula of u. Okay, yeah, maybe let me redraw the picture once more. So I have, let me write again, x of z of xt t would equals to x, right? That, let me, yeah, that's a formula, right? And then let me draw a picture again. So this is our point xt. And then we have a characteristic go up to this point. And the point that we're starting here is exactly the point z of xt 0, okay? Um, so that means that then we have the formula, right? We have the formula that uxt that we computed earlier by the method of characteristic. This is equal to g at this beginning point, which is z of xt plus t times the h of the z of xt minus h evaluated at dg z of xt. Okay, this is really beautiful because then we have a complete formula for u. Again, here, uh, uh, here, g and h are given to us as C2 function, right? And capital Z is C1 on Rn cross 0 up to capital time of t. So this implies that u is a C1 function up to time capital T. So we are done. It's a really, really beautiful result. We have to use the implicit mapping theorem here. Capital Z of xt is not totally determined, right? But it's implicit and it's there. Okay, so now let me end this lecture by a final corollary. Corollary for the theorem. So let me recall the theorem. It has been so long. Okay. The theorem was that uh, this red box, the first red box here is that for t equal to this one, so provided that the map is always invertible, then we can still define uh, uh, define capital T, right? So there's a remark saying that in some cases that capital T can be infinity. That means that the solution is defined everywhere. Um, um, it's defined everywhere, meaning that we can use the method characteristic to solve the Hamilton-Jacobi equation everywhere. This is very rare, but it does happen. Okay, so let me just write it down. The corollary say that let H and G be in C2 Rn be convex function. So we need to assume that it's convex. They are convex, okay? And again, assume dg and d square of g are bounded. Then the conclusion in this case that capital T is plus infinity, meaning that we can solve the problem everywhere. And it's very simple. So let me just write out quickly. Because there are C2 function being a convex functions that means that we have d square of h and d square of h and d square of g are greater than 0 as they are convex function. Okay, then this would imply that in is non-negative, is positive definite already. So if I plus t is a non-negative number, d square of h dg z d square of z. This one itself is non-negative definite, right? And in plus this is always strictly positive definite. So meaning that the determinant of this one is always non-zero. Okay. So for all z and all t greater or equal to 0, so this implies that capital T is plus infinity. That's it. Okay, so it's a long lecture, but it's great that we are done with first recalling the method characteristics for Hamilton-Jacobi equation, connect it with the Hamiltonian system, and second, that we were able to consider the case where the Hamiltonian is spatially homogeneous, and we can see that we have the solution defined for up to some capital T. And we have a rigorous proof for that using quite advanced knowledge on the um, inverse mapping theorem and implicit mapping theorem. Okay, so great. So let me stop recording.